Hello, everyone. Welcome to MIT's Energy Innovation Webinar Series. If you have attended the session last week, you know my name is CJ Guo. I'm a program director with the Office of Corporate Relations at MIT. Our office has a great industrial liaison program and a vibrant startup exchange platform through which we connect many of the world's most innovation-centric companies to leading edge research and to the innovation ecosystem at Cambridge here at Massachusetts. And I know many of you in the audience are with those companies. Thank you. I also many are also from the broader energy sector. Our sector today is facing unprecedented challenges with this globally spreading virus pandemic and historically low energy prices, resulting in a situation where if you talk with your friends in the industry, as I do, no company's business is in good shape today, and definitely complicating a already difficult transition towards a low carbon future. But we'll meet the challenges and hope come out of the other side in a better shape if we take effective actions. We take actions here at MIT by, at this difficult time, intensifying forward-looking engagement in technology development, innovation, and problem solving. That's the Industrial Liaison Program and the MIT Energy Initiative are offering this energy innovation webinar on a global basis. It's the second session of the series. Today we're going to focus on some critical low carbon technologies. Several of the leading experts from MIT will share their insights with us, not only on science, but also technology and the scaling up challenges. Hopefully through those effective engagement and potential collaborations, we'll be able to better navigate those difficult times for a sustainable future after the current crisis. Now I'd like to introduce our session moderator today, Professor Bob Armstrong. Bob is the Sorbom Professor of Chemical Engineering, and he is a member of both the National Academy of Engineering and the Academy of Arts and Sciences. He co-founded and has been leading the MIT Energy Initiative since 2013. And last but not least, he himself is an expert in pathways to a low carbon future. So no better person than him to chair today's session. With that, please welcome Professor Bob Armstrong. Bob, thank you.
Thank you very much, CJ, and welcome to all of you on the webinar. Good morning or good afternoon, depending on what time zone you're in. Thank you for joining this, as CJ mentioned, second in a series of 3 webinars looking at the challenges in transitioning the energy system. This is one of the major focal points at MIT across campus, and the Energy Initiative, MITei, plays a pivotal role as a hub to bring together faculty, research staff, student efforts aimed at transforming the world's energy system. So to help us meet energy needs globally going forward, and at the same time decarbonize the energy system and the economy so that we can mitigate climate change. Last week we did a lot of framing of the issues. We talked about the challenge itself and the contributions that are needed across subsectors within energy. So we looked across the power sector, the transportation sector, industry, and buildings. We looked at some of the policy issues in decarbonization in a post-COVID-19 world. material supply chain issues in the transition, and we also looked at some of the issues in the transportation sector, in particular decarbonizing urban passenger mobility. This week we turn to an equally important set of challenges, and those concern how do we, number one, provide energy generation. So how do we produce electricity, say, in a decarbonized world? And our first panelists are going to address that issue, specifically looking at fusion technology. Then we'll look at novel ways to improve energy efficiency. This is a general challenge that cuts across all of the sectors that employ energy, and is widely believed to be one of the keys to reaching our zero or net zero carbon future targets. And then thirdly, we'll look at carbon capture and sequestration issues, which again is an issue that's important for both decarbonizing the power sector and some of the large industrial emitters of CO2, but also in negative emissions technologies that could help us and play a central role in allowing us to come back towards a 450 parts per million or lower CO2 concentration globally, given that it seems likely that we'll pass that target in the not too distant future. So ways to come back are going to be absolutely essential. So with that brief introduction, I'd like to spend most of our time on the panels themselves. And the very first panel that we have is looking at very exciting work going on at MIT in the fusion area. And I think to many of you, we grew up in a world where fusion was the energy technology of the future. Always has been, always will be. That was the standard joke until recently, where some really innovative thinkers here at MIT and elsewhere have come up with some very interesting pathways to get us from the science we've learned about fusion to applied technologies that let us actually generate fusion energy commercially, potentially, within the next 15 years or so. This next panel, the first panel, is going to be comprised of Professor Dennis Whyte, who's director of the Plasma Science and Fusion Center at MIT, and Brandon Sorbom, who is the chief science officer at Commonwealth Fusion Systems, which is a fusion startup company that spun out of MIT just a couple of years ago. So I'd cut my introduction off at that because I think we'll want to spend our time listening to Dennis and Brandon.
Right, so this is a story. It's a story that has multiple components in it, but I thought for this audience that you would enjoy not just about like sort of the promise of fusion, but really about how you accelerate something like fusion, which is very much a hard tech endeavor, both through technological innovation, but also through what I would call organizational innovation, and really it has a lot to do with how you minimize the time in exchanging technologies between the laboratory, scale it up in some way, and then get it to a point where it can head it off into a nascent industry. So Brad and I will present this jointly between ourselves. Okay, so let's get this. So, you know, one of the fun parts of our story is that you know that you've sort of made it when there's a cartoon by Dilbert about what you're doing. And this actually holds in it a lot of the jokes that Bob was talking about, you know, the fact that, you know, fusion's been 15 years away and it'll always be 15 years away. But the fact of the matter is, it is true that really the landscape has changed. And that's actually why there are dozens of startups actually working on this now, being supported by many aspects of the private sector, including large-scale energy companies, venture capital, and so forth. What's interesting about this is that it's what I see is that something that was essentially solely a government program for many decades, is reaching that part in the knee in the curve when you understand that there's both the need and the opportunities which are there for it to be picked up, in fact, by the private sector, and that interest is growing. Nonetheless, there's still some skepticism actually about us delivering on the timescales of what we're talking about, and we understand that skepticism, and in fact, we've built an organization to take that on. So we'll start off with a really quick tutorial, like what is fusion? It's really simple. It's literally just the power of the stars. Stars are large balls of hydrogen, and at the center of them, they fuse hydrogen into helium and produce energy that supports all of us for billions of years. On Earth, we actually we fuse the heavy form of hydrogen, but in some sense that's a detail. In the end, we fuse the most abundant element in the universe into helium, and this releases staggering amounts of energy, approximately 20 billion times more energy per reaction or per unit mass, if you want to think of it that way, than chemical reactions. It's the reason stars run for such a long time. So why on Earth would we pick fusion energy? Well, that has no polluting emissions intrinsically, and no carbon emissions either. The fuel, because it's based on basically free, effectively, fuel supply, and it's essentially inexhaustible because it will last for hundreds of millions of years. You can actually generate the power anywhere. Also, another important one is you can generate it any time, so it tackles the challenges of intermittency. There's no meltdown is a physical impossibility in fusion devices because there's only about a gram of fuel being fused or burned at one time at any given time, and it actually avoids any long-lived nuclear waste. You don't have to worry about fissile material proliferation, and in the end, because of all these, you actually know that you can basically provide mankind's energy demands, forever, essentially. So all that sounds great, of course, but and it's scientifically feasible. I mean, we know this can actually work, but it has not yet been harnessed. In particular, of course, this needs to be harnessed in a commercially competitive way to actually realize what amounts to essentially energy transformation for mankind, actually, when you're using fusion. Now, one of the fun ways to think about it is an oil tanker. Like, how inexhaustible is this energy source? So if you take the water displaced by an oil tanker, and you filter out that, then this ends up to be about 40 liters of this special heavy form of hydrogen, which is naturally occurring. You fuse it like the sun does. That produces as much energy that is in the entire tanker of oil, but it does not emit a single gram of carbon into the atmosphere. So that gives you an indication of how inexhaustible the fuel supply is. On a more practical note, what does a fusion plant look like? It's like we talk about the sun because it is the process that is in the stars, but actually on Earth it's a rather technical, prosaic engineered system. So we build a device, in particular, that contains large amounts of electromagnetic coils. We confine this fuel at about 100 million degrees. The plasma fuses and releases energy. We surround, the energy is released primarily in uncharged particles called neutrons. But what happens is this just gives us energy to a material that you surround the star with on Earth that produces heat. And then that heat is extracted like a normal thermal power plant. And here's a cartoon that you can see. There's the person standing beside it. This one is a configuration for the particular brand that I work on called ARC. This produces about 600 megawatts of thermal power, about between 200 and 250 megawatts of electrical power. So you can see it's a rather compact unit. And in the end, if you just draw your box around this special part in the middle, which is the fusion generator, then the rest of this more or less looks like an on-demand, high-intensity, high thermal efficiency power plant. This is the reason why fusion is so attractive too, is because it doesn't require a reworking of the energy infrastructure that we have. You can more or less plug this into, in this case, an electrical power grid, but you can also use it for other things like industrial uses of heat, fuel production, all the things that we use heat sources for. Now, of course, the thing that you look at in this is that it's this particular one here, 100 million degree plasma, that looks like the kind of insane part, but in fact, that's a condition we've achieved in the laboratory already. And essentially, almost most of the physics requirements actually for doing this have been established in the laboratory. What has not been realized is actually an effective way to actually build this central part at a small enough and economically competitive enough way, and then to realize that into like a working power plant that actually goes forward. And that's actually what we're working on. So the conditions necessary are rather simple to think about. It's like building a bonfire. You basically put enough fuel together, wood, you get it hot enough, like by lighting a match, and then if you configure the logs in the right way, it basically keeps itself burning. Well, it turns out that's what we do, except we do it with this hydrogen fuel in this plasma state. The fuel is very, very undense. It's about 100,000 times less dense than air, but we get it very, very hot. This is actually why it's so safe, actually, in the end. It has in the end, it has an energy density about like the air that's in the tires of your car. And you can, and if you build it in properly, it basically confines this energy. Once these things are realized, it turns into like a SAR, because the fusion power keeps itself hot and is producing prolific amounts of net energy actually at that point. And that's actually the condition that we're going after. So we organize this in a particular way, which is a rather simple but robust way to look at it. We talk about the energy amplification of the system. So it's basically how much fusion energy we get out divided by how much it's required to actually externally apply to keep it hot. This has a simple figure of merit called capital Q, which is the energy gain of the system. Obviously, for a net energy system, Q has to be significantly in excess of 1, but it's also a scientific threshold, because when Q becomes very large, basically like a star, the plasma, the fuel, keeps itself hot by its own fusion reactions. So this is a funny plot that we organize this all onto. It turns out it depends only on 3 parameters. The temperature of the fuel, just for your edification, this 10 on this unit is about 100 million degrees. And then this is how dense the fuel is and how long we confine the energy. You can see here's capital Q of the order of 1. And so scientific break-even basically happens when you get past this point on this plot. And reactors and power plants live up here at Q greater than 10, right around here. So you can see these are actually experiments, including ones we did at MIT, which fill out this space, which you can see is very, very impressive. Like we're basically right up to the limit. We've also, in the laboratory, achieved temperatures well in excess of 100 million degrees. So really, this is our plan, is to take this configuration called a tokamak, which is basically a particular way that you configure the magnetic bottle, and actually move these blue points up into this region here to be able to demonstrate that. And once you're there, then you're really ready. That's a scientific threshold to get over, and then you're ready to talk about commercialization. You know, and also the other hit against fusion is that we've been waiting for a long time, and it has failed. That's actually not really correct. If you take a look in about 1970, around when the MIT fusion effort started, actually, that you can put this on a decadal plot, and you can see we needed a 30,000 times improvement actually to get to that magic place when you start making net energy. We actually built tokamaks at MIT to do that. That was called Alcator A. So that was around 1970. Around 1980, for the first time, we actually broke the triple product barrier in 2 of the products. It wasn't hot enough, but it was dense enough and it had a long enough energy confinement time. So that was really exciting, but we still needed another factor of 100 improvement actually at that point. And in fact, we capped this off a few years ago by increasing by yet another factor several decades. And now we're only within a factor of around 2 or less to actually get to capital Q of 1. And in its last days of operating, we actually set the world record, in fact, for fusion power density in these configurations, which is a key figure of merit of going forward towards commercialization and economic viability. So this beat Moore's law, if you're familiar with that, for processor chips and power. The frustrating thing a little bit is that, of course, you see this product got up to here, and really what was happening was the science became mature enough, but we were basically waiting for a breakthrough technology. And that's actually what's happened, is that if you take a look at where the science and programmatically where fusion was, is that we sort of figured out either we needed a technology breakthrough or you needed to build the devices extremely large. It wasn't really a science impediment, it was really a scale impediment. That's embodied in a project called ITER, which is very large. It's taking the world's governments basically to build it. And although its physics is very, very confident in it, it is slow and expensive. And it doesn't appear to be a direct path towards commercialization. Meanwhile, at the same time, the private sector was stepping in with concepts that were different than what I just described, but were being done at a rapid development pace, but needed to get there. So we sort of had this interesting situation about 4 or 5 years ago where we were in interesting quadrants of the development of fusion, but neither of them were really optimized. And so our idea built at MIT, was to actually put something up here that namely had high confidence in physics, that could be fast, small, and inexpensive. And that's exactly what we did starting about 2016 at the Plasma Science and Fusion Center at MIT. And the new opportunity was high field superconducting magnets. And I'll actually let Brandon take over from here.
Thanks, Dennis. So yeah, like Bob mentioned when he was introducing us, the big thing that changed was the underlying technology behind how you build these devices. So these fusion devices are big magnetic bottles that confine effectively a star inside of them by using a magnetic field. And so what happened was the old way of doing it was using these things called low temperature superconductors, which led to large devices like ITER. And in the last sort of 5 to 10 years, these high temperature superconductors have been commercialized to the point where you can actually go out from about a dozen vendors and buy wire out in the commercial market. And this wire, even though it's been made famous for having a higher temperature than the low temperature superconductors, what we really care about is if you look on the magnetic field axis, it can access much, much higher magnetic fields. So the impact of that, you can see that in the next slide. Basically, if you take the last 50 years of tokamak research, so that's almost 200 devices that have been built around the world of varying sizes, and you condense all of the experiments and the simulations into one plot, you get something that looks like this, that basically shows you the very non-linear nature of how the magnetic field affects the size of your device. So when you go through all the math, you can actually show that the fusion power goes as the magnetic field to the power of 4, which basically means, this size here is what we call the major radius of the device. And ITER is just above 6 on this plot. So the old way with low temperature superconductors was limited to a magnetic field of about 6 Tesla on the plasma. So you kind of had to climb up this curve. So these orange contours are this parameter Q that Dennis was talking about. You had to climb up that curve and hit 6 Tesla and then go up from there. And that leads to these very, very large machines. But with high temperature superconductors, you can actually open up the entire right side of this graph, and you can, instead of building a very large device, you can build a device that, the point that we start at with CMOD, then build a device called Spark, which would be the first device to demonstrate net energy from fusion, and then go slightly up the curve to build a power plant size device, which is still much smaller than even the demonstration device that would be using conventional technology. And so another really interesting innovation, I think, that had nothing to do with technology actually, was about the organization and the funding model. And so this is a quote from MIT's president that the MIT's greatest invention may be itself an unusual concentration of unusual talent, restlessly reinventing itself on a mission to make a better world. And we took a look, in addition to these technologies that were being made available, and we were driving the development of, we took a look at the funding streams. And traditionally, all the research at MIT had been funded by the government. And so in 2016, I was a PhD candidate here. And my research was, for part of it, was funded by the government. And so all of the tokamaks that Dennis mentioned that we had built were government funding. But starting in 2012, the government funding had started to dry up. And we decided to take a look at other streams of funding. And so here's a quote by Bill Gates talking about the importance of government and research institutions and private investors and businesses to all work together. And this is really an area where people talk about, this is, in the title of this talk, tech transfer. This is really a great example of that happening, where the government put in, about $1 billion worth of total investment into the labs at MIT and built up this just great foundation of research and infrastructure and the people who actually built all of these things. And then as the government funding started to go down, we were able to go out with the company that we spun out, Commonwealth Fusion Systems, and actually raise money from the private sector. We have investors like E&I, who's one of the big MITei members, the Engine, Breakthrough Energy, to name a few. There's about a little over a dozen investors in a coalition that came together, and we raised $115 million to start this company and then actually sponsor research back at MIT through MITei, which Dennis will talk about a little bit later. So we put together this partnership model. This was fresh off the heels of this record that Dennis mentioned that we set with the machine. We started this collaboration model with MIT. And we've been, for the last 2 years, we've been working to build up the magnet technology that will allow us to build Spark, which is the first net energy device. And so one of the things that really allowed us to get moving so quickly is that we like to say that Spark was born at scale. So this leveraged something like 200,000 square feet of infrastructure and lab space at MIT. And I think most importantly, Dennis will probably agree with me, is the people that already existed. So we started, we didn't start with, you hear about startups that start with a couple people in a small space. This is really, Fusion is a project that requires a lot of infrastructure and requires, a large team, even though our effort is a lot smaller than the big government programs. And so we were able to start on day one with all the lab space that we needed and a team of about 40 people that's now grown to about 120 people that are really working side by side on this project. And so we're actually now the largest project and privately sponsored activity at MIT. And this has really been a great model for collaboration in tough tech in general, because it allows us to kind of pick the best out of both the academic world and industry. We can hire from those two different pools. We can kind of leverage the best aspects of both of these things, and it really helps you. Something that's common term that's thrown around in startup land is the valley of death, where try to go from government funded research into something that is actually commercialized, and there's this big valley in between. And we think that this model really represents a way to do that quite fast.
Yeah. Hi. Yeah. So thanks, Brandon. Right. So just to come back to loop this back around, it's the way I look at it is that the MIT and CFS relationship is a unique collaboration because a little bit by serendipity, a little bit by planning, we actually literally built technology transfer into the entire organization. And I really have to credit MITei here in its role in this, because CFS is a MITei member. And it was brought in to do the research at MIT and at the PSFC under the MITei agreement. And what happened in this was, besides a tremendous excitement about the technology innovations which are occurring around these new magnets, we also provided a structure that allowed the teams to work side by side. We're actually inventing and building the needed technical innovations for fusion. And this came about from some clever ways of basically having an agreement that it had consistent IP protection, for instance, for both MIT and for CFS, and then indirectly the investors in CFS. And this is proving to work, because we're just under 2 years into the project. And in less than 3 years, this team is now on track to deliver both the key technology, which is the new magnet technology, and that will be world record producing superconducting magnets. But it also is going to produce a team that can produce those magnets for the Spark project. And it's because there is no, even though we're generating patents and so forth, the teams are working side by side to actually assure that that can happen. And then we hand off the technology from the academic side directly into the industry. The industry, once it becomes commercial, goes off and starts doing it in a commercial way, while on the MIT side, we're developing the next layer of the innovations and next layer of talent, which comes along. So, so we'll conclude there. But I guess one of our other points in this, because everyone in the team, everything that we do is built basically to speed. Because if you take a look at the history of such tech development, what often happens is it's the organizational impediments to actually getting that tech transfer to happen quickly. I think we've removed those barriers with the help of the Energy Initiative and MIT and our investors and among our teams. I think we've set up a model that actually is a very exciting one for getting from the laboratory to the marketplace in the fastest time possible. So we'll conclude there.
And ask questions. And while I'm doing that, members of the audience are welcome to send in questions in the Q&A chat that you'll see at the bottom of your screen. So I welcome that. One of the questioners wrote in saying they have 2 questions. It would be helpful if you type those in, and then I can ask those of Brandon and Dennis. So let me start off with a question, a very simple question, but one that maybe people would be interested in, which is you refer to 2 reactors, ARC and Spark. Where do those names come from?
So ARC was a name. Actually, I can blame Brandon for that, because he was the lead author on the paper that started with ARC. So technically, it is a acronym which stands for Affordable, Robust, Compact, because those are the primary features of ARC as a potential pilot plant for fusion that we thought were critical ones for marketability. Brandon can comment as to where it really came from, but we can't,
It has nothing to do with the with Iron Man or anything associated with the Marvel universe.
No,
Okay.
nothing. And Spark is a continuation of that, but Spark is something like as soon as possible ARC, or small and privately funded. It itself was another acronym that we love to play with. But in the end, I think it kind of makes sense. Spark it's literally the metaphor is that it is the spark for the fusion energy revolution. So, and Spark is and we didn't talk about the technical details of this, but Spark is the device that we're building now. We're building the technologies, the project, the site, and it's a joint project between MIT and CFS to basically show net fusion energy in the middle of this decade.
Yeah. So I'll get to some more serious questions now. So besides the magnetic field, which you've got this really nice innovation with these high temperature superconductors, what's the next? What is the next, or maybe what do you see as some of the key challenges beyond that?
You want to take that first, Brandon?
Yeah, sure. I think the next, after the magnet technology, the next kind of key challenge is in what we call the blanket, which is the system that surrounds the fusion plasma, and is in our design is a molten salt. It's similar to the types of molten salts that you would see in like a solar concentrator, like a power tower. It's a little bit different because of the nature of the fusion reactions. But I would say that technology is probably the next big challenge that we have. Luckily, we're not starting from scratch. There's a lot of technology available in both solar and actually in conventional fission. There's been a lot of molten salt design, but actually getting that done for a fusion design is going to be the next thing. But Spark actually won't have a blanket. That was part of the reason that we did this in 2 steps. A lot of people ask us, why didn't we just go straight to ARC? And it's so that we could have the time to develop all of the rest of the technology. Really, the biggest technological step that we needed to make was to prove out that we could build these magnets and these magnets worked and that we could get net energy. And then the next step after that is actually taking the power out of the device, putting it onto the grid.
So I have 2 questions related to Dennis's comments about, or maybe it was you, Brandon, talking about how you were able to start instantly at scale with Commonwealth Fusion Systems, and physical resources that a startup company, a couple of people in a garage wouldn't be able to do.
Correct.
So with respect to that, are there other energy areas where you see a similar need, or is fusion a one-off? I mean, typically the startup model is, a couple of people literally go off in a garage sometimes and work on the technology ideas. But in energy, some of this technology is highly specialized, and you need particular resources. I'm just curious, as you talk to others in the field, what are your thoughts on other technologies or other areas of energy science that could benefit from what you've learned here?
Well, I mean, Brandon can comment to other companies, but I mean, it's a sort of an obvious scientific point, is that it's the scaling which is almost the hardest thing in this. So it's not just the scale, of course, of evolving the first bits of the technology or the science. It's also having the robustness in the organizational structure such that this can actually pick up this thing and scale it to a product which is actually used in a large enough part of the energy segment that of course pays back investment, to the investors, but also starts making a dent in climate change. So, it's a little bit of the joke around when we talk about what we're doing, but it's actually not a joke. We basically have to build thousands of these, not one of those arcs. And that's actually what's going to make a difference in climate change, which is what everybody in our organization wants. I'll leave, Brandon can comment from the company side.
Yeah, I would say just really quick. You can see evidence of that in the engine. Actually, one of our fellow panelists is Shreya, who, even though they're not physically located at the engine anymore, they started off in the engine where we're also located. But there's actually several now energy-related companies at the engine, which is this big startup incubator / VC / accelerator that was also spun out of MITei. And so I would say, things like the technology that Via Separations is working on, another company that's working on energy at the engine is Form, in large scale, grid scale battery technology. So I do think this is a model that's applicable to a lot of different places, a lot of different industries dealing with energy.
Yeah. Yeah. Go ahead, Dennis.
Oh, I was just going to say, and I think what we're seeing is interesting, is that it's clear it should not be just a one-off, and it should be just a one-off, not just because there's opportunities in other energy parts, but also because of the synergies that you start developing with more companies that have this kind of structure, because you start building up a virtuous circle. It has many analogies to the beginnings of large biotech. Quite frankly, I mean, you can see it's got those things which are, because some of it's competitive and some of it's collaborative, but that kind of has the feeling for what it looks like around clean energy.
And do you have special workforce issues, as you imagine? You know, as you said, you don't need one of these. You need thousands of these reactors to deal with climate change. Do you see workforce issues that are going to be unique to this industry that's forming, or can you bring in workers from other industries? What industries would those be? What is your human supply chain look like?
I can actually try this one first, Dennis. This is actually why I think it's really great that we have industrial partners like E&I involved. Actually, is that really at the end of the day, we want the arc reactors to be a construction project that's kind of like building. Obviously, it's not it's not the same thing, but like building a platform or or building a refinery or something like that. It's a lot of steel. It's a lot of concrete that you have to pour. But a lot of the core technology actually is really, we're working towards making it so it's not this crazy high-tech thing that you need a very specialized team of people to build. That's part of, I think, the technology, getting the technology out into the market is designing it in such a way so that you can actually build it with workforces that exist already, that build maybe large projects, but doesn't have to be, we're not like, building spaceships. We want to build something that that can be mass produced.
Right, exactly. So what's interesting about our challenge is that, again, if I look numerically at it, I think we have to do exactly what Brandon said. If you look at the eventual deployment, we can't reinvent the wheel for this. This has to take advantage of existing people and organizational infrastructure in large-scale energy companies like E&I. It's why they're partnering with us. Yet at the same time, putting on my professor hat, is that the special skills which are needed to lead the technology innovations, are going to come from places like MIT, because there's still needed in this that drive towards competitive advantage, and that's going to come from a very special workforce consideration that has to do with people who are understanding the totalities of this energy system. So I think it's a dual-pronged challenge in this.
Great. So we have lots more questions, but we don't have a lot more time. So I'll start with, I think, a short answer question, which is, when do you expect to have a continuous reactor?
Yeah, so the combined goals of our teams is that we want to deploy those in the early 2030s.
Okay.
And to be clear, that what that means is that it's a commercial power pilot plant that is, for example, supplying electricity to a grid in a reliable manner. Great.
This is fascinating work, and we could go on for another hour or so just with the list of questions I've got here. But thank you both very much, Dennis and Brandon, both for the presentation, but also for this really innovative work and way of doing the work that you've talked about. So thank you.
Well, thanks for the invitation, and enjoyed it. Yep.
Yeah, good.